So back in video 10, I introduced the concept of tension and how much force or tension is in the string as we hang things or drag things. And what we're going to do today is look at how the angle of that we drag things influences the uh, the forces and the acceleration. So if you remember back a few videos ago, I had dragged my textbook. There it is. I got it all set up here. I got my Newton scale, and I dragged the textbook across the bench. So now what we're looking at is what happens as I change the angle. So instead of pulling this across totally horizontal, parallel to the surface of the table and level to the floor, I'm going to raise this at an angle and pull. How does that impact on what we have? Here's the textbook problem we just looked at. I measured the mass of the book and it's 1.1 kilograms, and I'm pulling it across the desk. And I looked at my Newton scale and I saw that I'm pulling it with a force of 6 newtons. And I used my protractor and realized that the string made a 30-degree angle with the desk. That's the angle of incline. So, what I'd like to know is the coefficient of friction. And the key piece in this really is that the book is not accelerating. And once again, when it's not accelerating, our net acceleration is zero. Our net acceleration is zero. So our net force is zero. And what that tells us is that the horizontal forces, the force going left and the force going right, I got those backwards, are equal. But when I draw my free body diagram, so I have my force of gravity pulling down, I have a normal force pulling up, I have a force of friction that's resisting the direction that we're heading. I pulled at an angle that was upward of 30 degrees. So the pink or magenta color here is at 30 degrees to the angle I pulled. This force equals this force if there's no acceleration. If there is acceleration, that'll help us determine the net force. But because I didn't pull it horizontally, things have changed. And we need to analyze this triangle right here. This triangle is going to be so important to us. So I've taken my triangle and I've drawn it down here just so we can work at it a little easier. And what I'm going to do, instead of writing my force over here, I need to remember that this is this side of the triangle. That's what that represents. So I'm going to write it here instead of at the end. And it's a right angle triangle. And what we're going to do is we're going to break this into its component parts. So the first thing I always do when I've got a triangle like this is I always label my sides. So once again, this is my adjacent side between the 30 degrees and the right angle. This is my opposite side, and this is my hypotenuse. What I'd like to do is I would like to use my trigonomic ratios and using my hypotenuse and my angle of 30 degrees, determine the adjacent and the opposite sides. So where do I start? Well, I know that the sine of theta equals my opposite over my hypotenuse, and that my cosine of theta equals my adjacent over my hypotenuse. And since I'm trying to find my opposite and my adjacent sides, I'm going to do a little bit of algebra here. I'm going to say it's my hypotenuse times the sine of theta equals my opposite. Same algebra, my hypotenuse times the cosine of theta equals my adjacent. Now I just put my values in. My hypotenuse was 6, and I had the sine of 30 degrees. That will give us our opposite. Likewise, the sine times the cosine of 30 degrees will give me my adjacent side. is 6 times the sine of 30 degrees, leaves us with 3 newtons as our opposite side and 5.2 newtons on the adjacent side. Now let's take those numbers back up to our free body diagram and see what that means. So this side here has a force of 3 newtons, and this has a force of 5.2 newtons. Okay? Once again, remember, this force is our applied force, and because there's no acceleration, that will equal our force of friction. So our force of friction in this problem is 3 newtons. The really interesting piece of this is this force. This is an upward force. It's an upward force. I could put it over here if I'd like. This is 5.2 newtons. We can figure out the force of gravity taking our 1.1 kilogram book, and multiplying that by 9.81, the force of acceleration on gravity. We have a force of gravity here of 10.791 newtons. This does not equal Fn. So what we have to remember is that our downward forces are gravity, but we have 2 upward forces now. We have an Fn, and we have this other Fa being pulled up. This was 5.2, and this was 10. I'm going to round it off to 10.8. So we can find the normal force. Okay, so once again, we had a force of gravity pulling it down, force of gravity 10.8 newtons. We had this upward force of 5.2 newtons. And then we also had our normal force. So in this example, our force of gravity is equal to the normal force plus this other force caused by the adjacent. I haven't given it a name yet. We will here in a minute. And if I want to know the normal force, I'll take the force of gravity and subtract that adjacent force, and that will give me my normal force. So in this example, 10.8 newtons take away 5.2 newtons is going to be the normal force, and that equals 5.6 newtons. The original question was to find the coefficient of friction. So now we know that the coefficient of friction was FF, which is 3 newtons of force, divided by Fn, which was 5.6 newtons of force. So we know that our coefficient of friction, mu, for this problem was 0.536. And it was significantly altered because the surfaces are not being pushed together as hard as they used to be, because we're lifting this book up a little bit because we're pulling upward. Now, the last important piece of this is we need to give these things an easier name. We're not just going to keep calling them adjacent and opposite sides. So this hypotenuse piece here is our applied force. That's where we're pulling. So we're going to call this one our applied force in the y direction, and we'll call this one here our applied force in the x direction. I've been trying to keep these videos quite short, so I've introduced the whole concept here of pulling at an angle. Now what I'm going to do is a few variations on that with a little bit of algebra. So if you've understand our concepts that we've done so far, and you've got some good algebra skills, you can solve pretty well any of these problems. But if you want to keep watching, I'll solve a few additional questions. The first one I'm going to do is, here I've got a sled with a mass of 18 kilograms. Let's just assume, it's some kind of crate, or maybe it's a sled with somebody sitting on it. And I'm going to pull that at an angle of 25 degrees. So what that's saying is that this angle here is the theta is 25 degrees. And we have an applied force, and I want to label this. We've got an applied force being pulled here at 70 newtons. And I want to know, what is the acceleration? So let's just make sure we've got our free body diagram done. I have a force of gravity pulling down. I have a force of friction. Oh, I didn't put my my coefficient of friction in this problem. Mu is 0.15. What is pulling up? Well, we've got a force pushing up from the surface, which is a normal force. But as we learned in the last example, we have another force pushing up, which is this force right here, which is our applied force in the y direction. We also have an applied force in the x direction right here. So we've got lots of things going on. And to me, the easiest, most important thing is we got to figure out this triangle. Now, the quick and easy is finding this force of gravity. We had 18 kilograms multiplied by our 9.81, which is the acceleration caused by gravity here on Earth. So this is going to be a downward force of 176.58 newtons. Okay, so the next thing I'm going to do is I'm going to figure out my FA in the y component. And from the previous example, we saw that that would be equal to the hypotenuse times the sine of theta. Okay, so sine, this is the opposite side to this angle here. So that would give us 70 newtons times the sine of 25 degrees. So our applied force in the y direction is 29.58 newtons. So now the question is, do I do the other one? And I think I will while I'm at it. I'm going to figure out my FA in the x direction. And that would be h, my hypotenuse, times the cosine of the angle. Once again, the hypotenuse is 70, and we're going to multiply that by the cosine of 25 degrees. And we're going to see that this equals 63.44 newtons in the x direction. I'm just going to put a little arrow reminding you, this is going this way, this is going that way. So I know what this other force is now. This force right here, if I was to grab that arrow for a second, this could be put here to help us remember what's going on. So the force of, need a pen. The force of gravity is equal to the normal force plus this applied force in the y direction. So from that, I could just move my applied force onto the left side of my equation, and I would know by subtracting what my normal force is. My force of gravity was 176.58, and my Fy, or my Fay, is 29.58. So I will see that my normal force is going to be 147. Now, if I want my force of friction, I know that force of friction is mu times Fn. So we would take our 147 and multiply that by our coefficient of friction. And we would find that we have 22.05 newtons as my FF. Okay, so once again, I now know that this force right here, I'm going to round that off to 22, and I know that this force over here is 63, By subtracting those, I'll find my F net. So our F net is my FA in the x direction, take away my force of friction. So once again, I have 63.44, take away 22.05. Once again, that's in that direction right there. And when I subtract those, I'll see that my F net is 41.39 newtons. Once I have my F net, we know that our F net is equivalent to the mass times the acceleration. So if we want to know the acceleration, we rearrange, and we see that our acceleration is 41.39 newtons divided by the 18 kilograms that we started with, and we have an acceleration of 2.30 meters per second squared in the positive direction. Once again, I've got a nice easy problem here. We're going to pull an object with a force of 692 newtons, and it's at some angle here we'll call theta. We see that it's not changing speed, so there's no change in velocity, which means that the acceleration is 0. The other critical thing that tells us is that our FAX must equal our force of friction. The problem is that we want to find our theta. We want to find what angle it's pulled at. And then one last piece of information that's super important is that the frictional force is 416 newtons. So once I know that this is 416, that tells me that this is also 416 newtons. Remember that this is a right angle triangle, so we see that the adjacent side and the hypotenuse, that's the cosine of theta. So our FAX is the adjacent, and our FA is the hypotenuse. So it's simply a trig ratio problem. We have 416 newtons divided by 692 newtons. That equals the cosine of the angle. So we could solve that by finding the inverse of the cosine. That will give us our theta. Punch some numbers into your calculator. For those that prefer the old-time trig tables, you can do that as well. And we see that the angle it was pulled at was 53 degrees.